Alright, today we will be working on problem 5-5. So to start out, we're given a sphere rolling down a hill, and we're given its rotational inertia, and we can express our answers in m, r, h, g, and theta, and h is measured from the base of the incline to the lowest point of the sphere, and r is the radius of the sphere, g and theta, sort of obvious, m also obvious. So we'll start out with part A by finding V, because we need V to find translational and rotational kinetic energy. So we'll use that potential energy equals kinetic energy. So mgh equals the sum of all the kinetic energies, so 1/2 mv squared plus 1/2 I omega squared, and we know omega equals V over R. Using some, we'll plug in all the given values, so 1/2 mv squared plus 1/2 times 2/5 mr squared, which is given to us as the value for inertia, over times v squared over r squared. The r's will cancel out, the 2's will cancel out. So and on both sides the m's will cancel out. So we're left with GH equals 7/10 by adding up the 1/2 and the 1/5. V squared. V squared equals 10/7 G. Now we can solve for the translational kinetic energy, which is 1/2 mv squared. And since we already have v squared, we can just plug that straight in, and it equals 5/7 mgh. Then for part 2, we're solving for rotational, which we know is 1/2 I omega squared, or as we found earlier, after all the canceling, it equals to 1/5 mv squared. And we plug v in there, and we get that k rotational equals 2/7 mv squared. Now for part B, we'll be finding the linear acceleration and the magnitude of frictional force. So for part 1, we'll use a formula to solve for velocity. It's not on the equation sheet, but it's a good thing to know. V final minus V initial, which is sometimes written as u squared, but don't get that confused with potential, equals 2AD, and where A is linear acceleration and D is distance. But since the initial velocity equals 0, it's just V squared equals 2AD. And we know from using the triangle and trigonometry that the distance equals h over sine theta. So v squared equals 2a h over sine theta, and then a equals, we can plug in for v squared, a equals 5/7 g sine theta, because the h's will cancel out. For part 2, we can use the sum of the torques to find the force of friction. So F, which is the force of friction, times the radius of the sphere equals the inertia times the rotational acceleration. So if we plug in for I, then we get F equals 2/5 mr squared times alpha over r. The r squared will cancel out with the r on the bottom, and we know that A equals r alpha, so this just equals A. So F equals 2/5 ma, and then we'll plug in A from the previous answer to get 2/7 mg sine theta. Sorry, sine theta. Part C, is really easy. You just use that the change in kinetic energy is equal to the change in potential energy, and since there's no more potential energy at the bottom of the incline from gravity, K total just equals mgh. Now for part D, the rotational energy, I'm not going to write this out because it takes a really long time. The rotational kinetic energy of the hollow sphere is greater than the rotational kinetic energy of the solid sphere because the moment of inertia is greater. And that is how you do 5-5.